We present Brainwear towards multi-modal garment integrated EEG. Brain activity has acquired an increasing interest in the wearable field. As we can appreciate, most current commercial wearable EEG devices have low consumer acceptance because they are neither aesthetically pleasant nor socially discreet. Additionally, studies with these devices are constrained to laboratory environments with restricted movements. The concept of transparent EEG was defined by Blechner and used by other studies to focus on a combination of features of mobile sensing applications, including self-applicable, motion-tolerant, near-invisible systems that are suitable for long recordings. In the wearable human activity recognition, EEG has already shown great potential. It has been used in several studies to provide information on many psychological and cognitive aspects. Despite that, none of these studies has seamlessly integrated EEG with other physiological modalities in a single embedded system. The wearable EEG enabler is the latest generation of chips integrating EEG analog frontend, such as the ADS-1299 that provides 8 channels in a compact package, replacing cumbersome circuit assembly. Open source toolkits, such as OpenBCI, provide hardware and software suites using EEG in a complete embedded system. However, if other wearable researchers want to integrate more wearable components, they will need to engineer the components into the EEG system, which has many limitations because it is designed to only host the EEG function, such as an outdated microprocessor. Using the opposite approach, we propose Brainwear, an open-source transparent EEG sensing module that is compatible with the Feather family and based in two major design considerations. First, simplicity, by packaging all the EEG components in a plug-and-play module, and compatibility with the open and popular standards, so that it will not be locked in by legacy technology. With our approach, the researchers or designers can choose their own controller and wireless platform and integrate the EEG function just as if any other embedded modules. We validated our approach with a soft EEG cap prototype and a study based on the common approach in neuroscience, the single embedded task with visual stimuli. The idea is to classify 5 different levels of memory workload: resting state with eyes closed, eyes open, and 3 states with increasing memory load, 1, 2, and 3 back. The figure shows the experiment time course in which only the windows in the capturing stage are considered for classification of embedded states, as the participants are properly engaged in the task. We employ the ShadowCompNet, a CNN-based deep neural network model commonly used in EEG, and perform one session-out cross-validation. The results show that the resting state and cognitive load states are well separate, achieving similar classification as other neuroscience studies with medical instruments. We finally demonstrate how Brainwear can be integrated seamlessly with other sensing modalities, such as a Force Sensitive Resistor and a piezoelectric within a single sensor probe. The embedding of the entire setup is presented in a baseball cap. This is the recording of a person wearing the cap, while performing different head movements and facial expressions. The experiment starts with head movements with eyes open, in which we can see that the FSR and piezoelectric reveal ballistocardiogram activity on the forehead. Furthermore, we can also appreciate that piezo and FSR complement the EEG signals by detecting gross motion artifacts such as nodding and shaking the head. The cap also allows to observe a well-known neural process called the Berger effect, that exhibits an increase in the posterior alpha frequency power between 8 and 12 Hz when closing the eyes. Finally, our experiment shows how the wearer system could offer information on the wearer's facial expression, whereas the EEG data would have been discarded as a motion artifact in neuroscience. To sum up, we developed an open-source transparent EEG sensing module that is pin-compatible with the Feather family. We employed a garment prototype based on the standard neuroscience that achieves performance on par with neuroscience state-of-the-art. Further integration with mechanomyography shows how EEG and other sensing modalities can be integrated into one wearable system to provide complementary information about users' neuron and physiological activities. In this video, we can appreciate the multimodal signals from the soft cap, while a person performs different gestures and head movements. We believe our approach will enable more out-of-the-lab research opportunities that combine neural and physical activities such as cognitive processes during sports activities. Thank you for your attention.